And the title is exploring the impact of hydrogen embrittlement phenomena on the ballistic properties of the material.
Oh, thank you.
Okay, so we start.
Thank you. So just briefly. Normally, we think that hydrogen embrittlement is much more pronounced at slower strain rate because we give much more time for hydrogen dislocation interactions. General speaking is correct, and we try to identify the effect of hydrogen or at high strain rates. That is why we did ballistic tests. So that is our setup. And we can place specimens, send the gun, and measure the outlet velocity. We have a sabot and a specimen. So we have two specimens. One is hydrogen charged, one is hydrogen uncharged. And we have different ballistic velocities. So this is the hydrogen uncharged specimen. We send the bullet and speed is 350 meters per second here. This is 500 meters per second. So we didn't see the fracture at 350, but here we have a ductile fracture at 500 meters per second. These are the fracture specimen after slow strain rate, the faster deformation velocity, let's say. And we have hydrogen charged specimens. So the camera captures the fracture of hydrogen charged specimen. And here we have also the fracture surfaces. And this is the graph of residual velocity after the impact. And blue corresponds to the hydrogen free, the orange for hydrogen in specimen. For example, here at 450 hydrogen free specimen, we didn't observe the fracture, but it is hydrogen in this specimen. So these are the graphs. So we can talk about also hydrogen embrittlements under ballistic loading. So we did several microstructural investigations. So we're not sure about the mechanism yet. Maybe lots of dislocation just sweep the hydrogen and localize them in specific region, which can reduce the cohesive energy, etc. We need further analysis, maybe TEM, maybe some modeling. But we did 3D laser scanning image, so hydrogen just decreased the depth of the fracture surface. And yeah, like hydrogen uncharged specimen at low speed, we came up with some voids. And for hydrogen uncharged specimen, we kind of observed deep cracks, some moderate cracks with some dimpled surface, but hydrogen charged specimen, we have bigger cracks, deeper cracks, and more like cleavage facets. And yeah, we did some FEM analysis to capture the residual stress graph that I just shared with you. From slower to faster, we performed the FEM for both hydrogen charged and uncharged specimen. And we got this residual velocity versus strike velocity graph with hydrogen charged and hydrogen uncharged specimen. The damage parameters were challenging for hydrogen charged specimens. So we had another study that captures the effect of hydrogen on fracture locks. So we kind of did inverse analysis and got parameters from the literature for hydrogen uncharged specimens too, and perform our FEM analysis and came up with these results.